Okay, should be all good. Okay, any question from this time? We are starting on our very technical proof of lower bound for the not quite over algorithm, lower bound for the search problem. And we'll see later that this is also equivalent to the OR function. So we are just starting over the high level idea of this lower bound on search problem or proving the optimality of covert algorithm. And okay, yeah. So if there is no quadrant, then let's try to let me check. Okay, so let's try to go through this lower bound. So we were using this. Okay, it's pretty similar. Okay, yeah. So the idea is that we are basically introducing notations here. So we are tracking how the quantum state evolve when you go through the algorithm. So the algorithm starting with the O0 state, then we'll do some inventory that's independent of your oracle. Then you will do your oracle, then you do some inventory, then your oracle, etc. And let's say we do total K oracle, or actually we'll do big T oracle, but we'll kind of interchange. Let's say we do big K oracle here, and small K oracle here, and we end up with using another inventory, then we do measurement. And so the notation here is we have this psi f subcasing. This is the state that is the state of the algorithm that after, so there's this sub k means that you are ending after the I should say k plus 1 or I say sorry, it's a state after uk where it's a little confusing because we start with u0, but it's basically the state you get after it's a state you can get using k oracle calls, right? But so it's after the case oracle call, but also we also include this extra inventory, doesn't really matter, but we define it this way. And, okay. So at high level it's the state after case oracle call, and also have this f. That means your oracle is corresponding to a binary function f. And once again we think about f as a function from small n bit string to 0 and 1, and if we write out its truth table, then it's a big N bit string where big N is 2 to the small n. Okay. So we think this small f is a function, but this whole truth table is an input to our problem. And then we have another big F is another function that we'll try to solve, which is say the search problem here. So for example, the lower bound we'll try to run, the big F is this decision version for search or the OR function, OR. So the input is this big N bit string small f, and our big F will try to determine some property of this small f with minimal query to the truth table values. And for the search problem, well, it's a decision problem, so there are yes and no. So for yes, we want to answer yes when there is any 1 in this truth table, and we want to answer no when everything here is 0. Okay. Just see whether there is a 1 or not. And now the query complexity is how many of those truth tables you need to look up. And you can kind of convince yourself that classically you need to basically look up everything to make sure that there is no 1. Right? Everything is 0 here. And we are a little sloppy, but the quantifier here we are always working for worst case. So our algorithm need to work for every input. Okay. And yeah, so this is small f and a big F, and we are tracking those states. So why are we tracking them? Because we want to separate the yes instance and the no instance, right? Well, we need to do those queries because we need to make sure whether our input small f is going to. So we want to determine big F of small f, and we want to determine whether this thing should be yes or this thing should be no. Okay? So for some of the small f, you should at the end of algorithm you should answer yes, and some of them should answer no. And we have this mental picture of the Hilbert space, right? So this is a Hilbert space of every qubit in our algorithm, and everything kind of starting with the same state, right? So before you query everything, so before you do any query, then your state of algorithm is somewhere in a Hilbert space, and well. And because you haven't queried everything, so for every small f, it's the same point. And as the algorithm you evolve, then you should find some information about your small f with those queries. So you think about your states should start to diverge for different small f. And so this is the starting point, and what about the end point? And we should see today that at the end point, if you want to have a good probability to separate yes and no, and usually we do like a 2/3 probability of success. Well, yeah. So if you want a good probability to separate them, then that means everything in every small f that's a yes instance, and every small f that's a no instance should have a pretty big distance between that. And so now we have kind of the starting and end point of our argument. So let's start with small distance and end with big distance. Then if we can say that each of those OF don't increase the distance too much, then we can say we need to do a lot of OF to actually separate them. Okay. And then yeah. So now we go into a little more detail, and so we say distance. So what is the mathematical form of the distance we actually use? It is this thing, right? So this is a bit funny. It's so when we track the distance between two different f, we just use this vector psi f, and then minus the vector psi f prime, then take the distance. So this is, well, calculating this thing is easy. This is basic vector algebra. The vector minus the vector is another vector, then you take a non-square of this vector. So say a little something a bit confusing is, this is kind of funny for distinguishing quantum state, because you think about vector A and vector minus A. Those are actually the same quantum state because you know the global phase doesn't change your quantum state. But if you take this formalism, then A minus A is like 2A, and then you take a norm, it's very large. So this is a bit funny, but it works in our proof, so we use it. And anyway, so that's some digression, hopefully not too confusing. And you can also see, so if you expand all this square, if you expand all this absolute square, then this is basically equivalent to the inner product, because you have a squared, b squared, both equal to 1, then you have a cross term, that's this inner product. So those have a linear relationship. Anyway, we use this. It's pretty nice to use in terms of the arithmetic. And so what's good about this? So we say something about it, but there are something good. Something good is that this thing doesn't change when you don't do any oracle. because we want to use this to track how many oracle we use, right? So this is a very good property we want. We want that when you don't do any oracle, this thing doesn't change. And I'm skipping a little. Okay, but it's here, right? So this is the base property. I don't know. This is the property of the unitary. So this is a vector, then you apply unitary on vector, its length doesn't change. Okay? So that's cool. This actually track how many oracle we use. And as we said, at the start, this thing is 0 because every state is the same, the difference is 0. And we'll show much later part of today that, so this argument we can make it very precise. That if you have a way to distinguish those two, then this thing is actually large. Okay, so at the end we know this quantity will be large. But now, can someone close the door? Yeah. Yeah. So those have been covered. Okay. Then now we go to something a bit more confusing, I guess, but for justifying our construction. Okay. So a little confusing detail is, so we want to track this thing, but there are typically there are many non-instances and there are many yes instances. And so which of those f and f prime we should pick? Okay? But in our case, there is only one known instance, so we'll pick that one known instance. And but which of those yes instances we should pick in tracking this thing? So actually, if we just write down, just pick one f prime, it's not enough to do this lower bound because this is just classical, right? Because you can just do like a very classical query. So you are trying to distinguish whether things are all 0 or like 0, 0, 1, 0, 0. Then if your algorithm happens to look at this location, then you will distinguish those two strings with one query. Okay. So that's classical, and that same thing should happen in our quantum thing. Yeah. And so if you write down this in quantum way, then you can also see this happen in one query. So maybe this will help a little. So we'll say, I shouldn't. So we have this and this thing. So our non-instance and one instance differ here. We call this x bar. So if we have so if there are some state, psi, so if our psi is just x bar, right? Then we apply our OF, so OF0 and OF, sorry, we are not using this notation. So OF and OF prime, right? X bar. And then this thing, so we are thinking we are using a phase oracle, and then this will do nothing and it's still x bar, and this will become minus x bar, because we are doing phase oracle. And so the distance goes from 0 to 2, right? So our funny way to tracking distance actually is useful here. You track this global phase somehow. Okay. So then I should write somewhere, right? So the d change from 0 to like absolute value to x bar square, which is actually 4. Okay. So you see that d will change a lot if you happen hit the point x bar. But that's because you only pick one yes instance here, right? So we'll do something that when you do the classical proof we want to do, So we want to say you should be able to separate this no instance and a lot of different yes instance. So we'll say yes instance, say it only have one, but that one can be at any place. Maybe the first one, second one, or the last one. Then if you want to separate all of them, then classically you can say you need to actually look through all n places to separate them. And then you translate that, not really translate, but we have a similar flavor in our quantum argument, saying that if you want to separate the quantum state corresponding to this and all those different ones, then you need to do lots of quantum query. And so in more precise notation, it is, so we have our DS measure being this difference, and I forgot the square, so let's keep it back, edit it back here, okay. And this square, and then we just sum over all those pairs, okay. So this is the thing we'll check. So we'll check the distance between the psi f sub, I should say k because we're going to use k. Okay. The psi f sub k, and then different f prime, where f prime is either 1, 0, 0, 0 or 0, 1, 0, 0, so there is a 1 somewhere. So we sum over all those different f prime, and then we sum over those distance squares. So this is a thing we'll check, and we know each of those terms start with 0 and end up with some constant. And we are going to say the summation of those distances doesn't change too much, because say if you do this stupid thing of query at x bar again, right? So if you do this x bar query again, then only this pair will get changed a lot. This pair will change the distance from 0 to 4 as we showed, right? But all other pair doesn't change, because for all other pair, like if you query the first location, then all other pair, the query is always the same, so the distance doesn't change. And yeah, so that's how we'll show it. Any question for the very long scale, high-level sketch of our proof? Otherwise, we'll actually run this with numbers. Okay, not quite numbers, I guess more detailed notations. But anyway, so let's run this proof. And then we start with, well, once again, more notations. Okay? This is annoying, but I think it's not avoidable. So let's run to this little updated slide. Yeah. And yeah, so as we say, we will run this argument between this only no instance and big N different yes instance. So it's obviously there are big N different yes instances here, right? And okay, so let's give the no instance a special name is called F0, also called tilde because something stupid. So let's call the no instance F0 tilde, and that's the O0 function. And then we give all our instance some name. So so this is where you see why we need tilde here, because x start with 0. But anyway, for every x from 0 to n minus 1, then we define this fx. We still write it in function form, right? F sub x. This function is defined such that it's 1 when your input is x, is same as e sub x, and is 0 at everything else. Okay, so if we write down here, so this will be f sub 0, then this is f sub 1, and all the way to f sub n minus 1. Okay, so we're just giving the yes instance and no instance names. Oh, sorry, this is no instance and this is yes instance. And as we say, we'll consider all pair between this f0, f tilde 0, and f sub x. for every x from 0 to n minus 1. And we'll use the face version of Oracle. And we have, okay, let's write it here once again. So the face version of Oracle will have all f of x equal to minus 1 to the f of x, right? And we say this is losing some information because you should usually have a control, but let's ignore that for now, and guess maybe we can do homework here to show that if you add back control, it doesn't matter. Okay, so for now, let's assume we only have this no control version of Oracle. And now let's see how this thing actually is when you, because we have a very restricted f, when we put our f here. So a very nice thing here is our f tilde 0 is very simple because it's 0 everywhere, so actually don't do anything, right? So for every computational basis state, this is minus 1 to a 0, and that's just 1. So our Oracle, where our input is audio string, is actually, excuse me, identity gate. It doesn't do anything. Okay, this will simplify our calculation a lot. And what about is some f sub x? Okay, so f sub x of y, well, is almost identity everywhere except when x equals to y, right? So this f of x. Okay, it's a little confusing because we have x here and y here. But anyway, so this f of x is actually this f xy thing, and it's equal to 1 only when x equal to y, because that's how we define our small f. And then this thing, we have seen something similar where it's actually a reflection. Right? We have seen this thing in our upper bound global algorithm. So this is one. This has no phase for every y except for minus 1 phase on x equal to y. So you can, it's actually a reflection around this x. Right? And you can check this equal to this. Is when y doesn't equal to x, then it's just identity on y. And when y equal to x, this is 1 minus 2 equal to minus 1y. Okay. We've seen this about third time. And okay, so those are nice things to remember. And we also simplify our notation a little more, because those are the only Oracle we need to use, right? And so OF tilde is just identity, so we're just not going to write this anymore. And the OF of x, this f is a little extra, so we just write either OF x or write OX. So this is just we're being lazy about our notation. Okay, then we do a bit more formal. I guess it's not really more formal. We write this definition about psi f k again. Okay? So once again, we assume our quantum algorithm is run on this thing. So it starts with the O0 state, and you do some unitary, and you run oracle, unitary, oracle, etc. And those unitaries are called U0, U1, OA. And now we are saying end with big T, U big T. So we do big T oracle calls. Okay. Okay. And so we define our psi once again. Okay. So we have our psi fk, that is you run the algorithm after uk. So about, remember this is a case oracle call. Okay. So it's a state about after case oracle call, but also after the extra uk. And so that's psi fk, and if we say our f is this one of the yes, so this f sub x, then then the corresponding state will just be this, right? So remember we just defined this OX, that's just O F sub X. So we really do nothing here. So for this thing, we are just doing this lazy notation on the left hand side and right hand side. So instead of saying psi f sub x k, we just calling psi x k because we don't need to write this x. Okay? And the right hand side is the same thing. Instead of saying O sub f sub x, we just say O sub x. Okay? So here is just a notation, and we are being a little lazy on both sides because we know everything can be just parameterized by this number x. We only care about bigger and different f. And so for this O f tilde 0 thing, we are being even lazier. We just don't write f at all. Okay. So here we just say, instead of calling this psi f tilde 0k, we just say it's called psi k. Okay? So those correspond to yes instance, and those correspond to no instance. And there's only one no instance, so we just call it psi, to make notation easier. And on the right hand side of this, a little thing happened. So and we just realized, so we just using this, right? So it should have O f tilde sub 0 here, but we know O f tilde sub 0 is identity, so we just don't write it because its identity don't do anything. Okay. So nothing much happened here. We just rewrite our psi fk notation again, and then as we said, we will track this progress function, which is the difference squared and sum over pairs, and we gave it a name as d sub k. Okay, after k step, and yeah, so it's this non-instance state, then subtract with yes instance state. Yeah, and non-square. Then we want to sum over all possible yes instance state. We sum over this x. Let's do this thing, right? This x is what we sum over. Okay. Yeah. And then we make this even lazier. We think keep writing this k notation is annoying, so we just don't write this k. But you need to think about all the side. You should remember that all those side vectors. Anyway, we are being very lazy, so we write psi k dot psi. So we say our dk is this sum over psi xk minus psi k, and sum over and absolute value square sum over x. Any question? No? Okay. Then it should be about on time. Okay, no question. Then we do this high level summary once again. Okay. So we have our starting and end point. So this should be really 3 points, but we summarize the first point here. So one thing we'll be talking about is d0 equal to 0, right? And it's assumed here. So the first point tells us that how slow this progress function dk grows. And we're going to show that it grows slower than k squared. Right? So after k step, this will be some constant times k squared. So it's actually above 4k squared. We're going to show. Okay, so that's how fast this thing can grow. And this also includes that d0 equal to 0. So that's one thing. And the other thing we are going to show in more detail is that at the end, this thing will be about order of big N. Because so the intuition is that there are big N terms here, right? And each of them, because once again, this is yes instance, this is no instance. So state in a yes instance and a state in a no instance should be pretty far away from each other, because in the end you should do a measurement and you are able to separate them with a constant gap. So at the end, this thing is constant and this only grow is quadratic. Then we have this lower bound on number of steps we need to run. Right. So yeah, so it's here. So t squared should be about big N, then t should be at least square root n. That's the idea. Okay, so let's go to more detail. We are going to run through this 1 and 2. So first one, y is dk over k squared, and we are actually going to say show dk is smaller than to 4k squared. Okay. And this is a less intuitive way to do, but very rigorous. So we are going to show this by induction. Okay. Hopefully you can still get a intuition why this works. Anyway, induction. So induction means we are going to show this is satisfied at the very beginning, and that's true because on the first step where k equals 0, then dk equals 0. Okay. And yeah, this we didn't show again, but it's very easy to see. This we have been argued a lot in our high-level sketch. It's because everything starts with the same state, right? Yeah. Oh, sorry, I should do this with this. Yeah. It's just because our mental picture, and also you can see algebra very easy that everything starts with the same state. So at the start, the distance is just 0. And then we will run induction steps. So we assume this is true for some k, then it is also true for some k plus 1. Okay. So what we'll do is assume this is true k on k, then it's true for k plus 1. Okay. Then what we need to do is we need to calculate what is dk plus 1. And we want to write this kind of in terms of dk. So what we are going to do is we'll calculate the difference between dk plus 1 and dk. And we'll show this is not too big. And okay, so then now it's just algebra time. So dk plus 1 is, well, this psi x k plus 1 minus psi k plus 1. And okay, so let's see. Okay, it's still easier to run this, right? And so remember psi xk look like this thing. So it's u. So and it's psi k, and then psi k plus 1. We will do another ox here and uk plus 1, right? So psi k plus 1 is just this psi k, then times another ox and another u. And psi k is very similar. So psi k is this thing, then you want psi k plus 1, you add another uk plus 1, right? Okay? And okay, let's not erase for now. And yeah, so that's how we write. So psi k plus 1, psi sk plus 1 is psi sk. Then you add another layer of O and U. And for psi k plus 1 is psi k, then you add another layer of U. Then it's this thing. Then first thing happen. So we see this difference is this uk plus 1 times this thing, right? Both of them have this uk plus 1 extra. Then as we have been arguing on a high level, this non-squared is not changed by this uk plus 1. So we can just get rid of this uk plus 1. That's good. And then we do something smart on the next step. There are intuition to as to why we want to do this. Okay, let's say the intuition. So here we have two terms, and their difference is kind of hard to know. So we kind of do a hybrid here by adding and subtracting a term. So we have minus OXIK here, and we add another OXIK here. Right? So this is exactly equal to this because we are adding one term and subtracting the same term. But now this is cool because we are basically breaking this distance into two terms where, how should I say? This is it's hard to say. I guess we'll see how this works. So we break into those two terms, and this term has psi xk minus psi k, and multiplied by this OX. Right? And this term has, well, OX psi k, then subtract psi k. Okay. And now we do non-square, and so why is this good? Because now here we have psi s sub k minus psi k. Then this is basically dk, right? Remember, d is the distance between psi xk and psi k. And then this term will be will basically control how the progress grow, but okay, it's hard to convey the intuition, so let's just let's do the calculation. Okay, so we will bound those terms. Yeah. And anyway, so now we have two terms, and they have some intuition behind them. This is about decay, and this is about the actual change. And anyway, but we can do the mathematics. So mathematics, we call this term B and this term C. And now we do some not quite triangle, I think it's Cauchy-Schwarz. But anyway, we do some basic arithmetic. So we have b plus c squared, and remember b and c are both vectors. And then last will be, so we expand this out. B plus c squared will equal to both vectors, so will be equal to b squared plus c squared. B squared plus 2bc inner product plus c squared, right? This is vector calculation. And then you do Cauchy-Schwarz, so you know this inner product can be upper bound by the normal b and the times normal c. Okay. So then, from Cauchy-Schwarz, we know the vector b plus c squared is less than b squared plus so c squared should be outside. Yeah, less than b squared plus c squared plus 2 non b non c. Okay. And then we bound the b and the c one by one. And so so we do C first, okay? This C, and this is very crowded, so let's erase this first. And C is where we see that the quantum query don't, although it seems like you can query everywhere, it don't actually increase the progress too much. So C is OX minus I times this psi k. Remember psi k, well, anyway, psi k is a non-instant state. And anyway, so OX minus I times psi k, but OX is almost identity. Now we just need to remember, right? OX is this thing, right? So OX minus identity. So this thing is OX. Yeah. So OX minus identity is minus 2 projected onto X. Okay. So OX minus I is also actually very simple. It's just minus 2 projected onto X and psi X, and then you can combine this thing. So yeah, then you move this a little wrong, then it's minus 2, then inner product being X and some X. Then actually okay. C, okay. Then C is this. So okay, I'm skipping a few steps here. Okay. And but anyway, so C is like this. Then we are from here. Then we want to break up into those 3 terms, right? The b squared plus 2bc and c squared. And so b squared we skip here, but so b is this thing, but b squared, as we say, unitary doesn't change the non-square, right? So when we do this b squared, then we can just ignore this OX. Okay? So that's why this hybrid is really cool, because you can just get rid of this OX here. We want to make our dependence on X as little as possible. So I guess on a technical level, when we do this, we are able to separate this OX times psi X, because less dependence on X is the better. The less dependence on X, the better. So we kind of transfer this OX from multiplying psi X to multiplying psi K, and that makes things easier. And anyway, so when we do non b squared, that's just this psi x sub k minus psi k non-square. And we know that this is going to become dk once again when we sum over x, because that's exactly the same form. And then we have, so it's easier to say so c is this thing, so I'll just write down there non-c, right, is equal to, well, known 2 is 2, and known x psi k, right? And so known c should be a number, and known x, this is some computational basis there. But anyway, that's just 1. Okay? So this is known c. So we have our 2bc here, and known c squared will be 4, and this thing known square. And but we are writing sigma known here because inner product is a number. So inner product is a number. So for number known, we use a single line, and vector known, we use double line to make things, I think, a little clear. Okay. So known c squared is just 4, and is known square, and the inner product change the order doesn't matter. And finally, we have 2 non B and non C, and 2 times 2 equal to 4, and it's this thing. Okay. Okay. Everyone follow the calculation. And 1 minute. So then we see the real cool part. So so 1 minute we can finish this page. So here we see that then we are starting going to consider how everything sum over x, right? Everything sum x here. So for the last term, sum x is actually something very simple. So sum x, all the amplitude of psi k on x, then that's just norm of psi k. And if you want to see this in longer calculation, then you can write this norm as the inner product psi k with x and inner product of x psi k. Then we play with our Dirac notation. Then we separate this middle part into a projector onto x, and then we see here all other things doesn't depend x, so we can put the sum x inside. And if you sum overall computational basis state, this is identity. So then this thing is just psi k inner product with psi k, so this is 1. Okay. And yeah, we'll continue at the next class. 对，因为还没有 update， 但是其实可以点进去，就是都在 YouTube 上面。都在 YouTube 上。对啊，那个点进去也是 YouTube 的 link。哦，我没有点。我好像也没有，对啊，这是你要 update 啊。就是在这个频道里面。对啊，都是同一个频道，所以其实去频道找就有了。好，谢谢。
F 跟 F prime 要怎么找
？F 跟 F prime 怎么找啊？
我也不太清楚。
这个是其实没有什么好的找法，就是你依照你要设计的问题，你要去就是你要去选你觉得比较难分出来的 F 跟比较难分出来的 F prime，就其实没有什么好的找法，对吧？但是这里我们可以说是我们找的 F 跟 F prime 是这些东西，F 就是 F 也反正也只有一个可以找嘛，然后 F prime 就是我们找，但是说没有办法，但是你就是想要去找说看起来比较难分出来的东西这样子，对啊，F prime 就是因为 F 都是全部都零的嘛，那么像 F one 就是也是几乎都是零的，那就是只有一个一这样子，然后有很多个不同的一的可能的位置，所以我们就觉得它们很难分出来。然后如果你去看 paper 的话，是有一点 generalized 的，可是我有点忘记，但是就是基本上就是你会去看就是每个 query 的位置嘛，然后你会希望说，你每 query 一个点，你又分出来的 F 跟 F prime 都不太多这样子，有个，
太多这样。
我想想看我怎么讲，我确定我没有讲错，像是这里我们会说，就是有一个，有一个推导是说，如果你找出一坨 F 跟一坨 F prime 嘛，然后假设这里有，这个不是零，这里我想想看我要怎么画比较那个，我们这里有一堆 F，然后这里有一堆 F prime 这样子，然后假设全部连起来好了，比较简单一点，因为我有点记不太清楚，对，那我们会需要的 query 数量会是有点像，这里有 n 个东西，这里有 n 个这里有 n prime 的东西，然后我们会是 n prime 除以 l prime，然后 l prime 是说 l 跟 l prime，想讲 l 比较简单吧。L 是说你去看这里的每一个点，然后说你最多看某一个点，你可以发现它跟有多少个 F prime 不一样。那这一块就是一个，对。然后 L prime 就反过来，就是说你看所有的 F prime 的东西，你去看每个点，你最多可以看出有多少个 F 跟你不一样。对。所以会有这样的一个 quantum lower bound。我确认一下我没有讲错。找 paper 把意思的 quantum were bound by quantum argument 这个对，所以是有 paper，我们长不太一样哦，对，就是这个感觉，对啊，所以它大 X 跟大 Y， 对，它这写的比较正确一点，它是大 X 跟大 Y， 我们是说 F 跟 F prime， 但是其实是 set of F 跟 set of F prime 嘛，对，然后，对啊，然后他说我们有这个 F 跟 F prime 之间，我们有一个连线，这个就是我们有一个 set of pairs。然后那现在有4个数字嘛，我们最后结果也是 n prime l 除以 l prime 看更好。然后 n 是看一下有没有说错 ，n 是说 OK， 所以因为它连线可能比我们复杂很多，我是说全部连起来。他说在 x 里面的，说画一下吗？希望你看到。他说 x 里面的每一个至少都要连到小 n 个 y。对，还是可以用我们的 global 来讲嘛。所以我们的 x 如果 x 是 no， 然后 y 是 yes 的话，那我们的小 n 就会是大 n， 对吧？因为对， 我们小 n 每个 x 都有连到大 n 个 y， 然后对回来，每个 y 至少会对到 n prime 个小 n prime 个 x， 那我们的 n prime 就会是1。对，然后接下来有这个奇怪的 L 跟 L prime， 然后看一下我没有讲错，所以对某个 x 至少，对每个 x 最多有 y 个东西 ，OK， 对每个 x 的每个 coordinate 去看，最多都只能看到 L 个不同的 y 跟它一样，所以我们的 L 就是1嘛。就是你看每个点都一个不一样，然后对，那看有没有讲错，然后一样反过来这个 L prime 就是 y 的看回去，对，所以会有这样的 bound， 然后如果讲更细的话，就是这个其实也不是 tight 的，然后有些方式你要用更奇怪的方法去帮它，对，但是这是一个广场多帮的方法。Okay. Any other question? If not, okay, let's erase this. If not, then let's keep our derivation of square root and lower bound. Okay. So once again, we have our progressive function dk plus sum over x from 0 to n minus 1, the non-square of psi x sub k minus psi k, where psi k is really kind of psi k0, it corresponding to the only known instance, and psi sk corresponding to, after case query, the quantum state when your input is only have a 1 at the x location. Okay. And anyway, so we have this very detailed calculation. We are calculating dk plus 1, and we write it as this summation non-square of some b term and a c term. And we say our c term is just the inner product of psi k and x. And then if you sum over this inner product psi k x squared with all different k, then well we say it's 1, and another way to see this is 1, this is the probability of you measure psi k on a computational basis, right? So this is the probability you measure psi k on computational basis and get result 1. And so all the probability sum squared should equal to 1. Okay. And then we do another Cauchy-Charles to deal with the middle term. So the middle term looks very ugly, so this weird thing with sum x. And we break this up to basically the first term and the last term by this Cauchy-Charles. So we see we have a sum over x, and some term depend on x, we just call it a sub x, and something also depend on x is b sub x. And Cauchy-Charles says this is less equal to square root of sum x ax, square root of sum x bx squared, square root of sum x ax squared, square root of sum x bx squared. This is just Cauchy-Charles. And so if we write Cauchy-Charles, then we don't have those two weird terms multiplying together anymore. So that's very cool. We have square root, then sum x ax, sum x bx. And then we see that, well, those two terms we already see, because this is actually a b squared, and this is actually a c squared, right? So this is 1, and this, as we say, is dk. Okay. So finally we get what we want. This is the most important thing. Okay. So basically this, well, this is the important thing we want to derive. So we see the change in your progress at each step is less than, well, order the square root of your progress. And well, just from here, then you can do some algebra, and then you will show your decay. Then you will show your decay need to grow about order k squared. Okay. And anyway, so we have basically have done this calculation in the back of our mind. So then we are already assuming decay is bounded by k squared, bounded by order k squared, and we just prove this by finishing induction. Okay. So finally, we are going to use our induction step. Induction step says that our decay is less than k squared. Then we plug in this back here. So we have decay plus 1 is less than, because we set up all the number nicely, so this is 4k squared, and 4 square root decay is 8k, and you have another 4 here, so this is 4k plus 1 squared. Okay, so now this is the finishing of the induction. Question? Right. So we show that for every k, decay should be less than 4k squared. Okay. So that's the bound upper bound on how fast decay can grow with k. And finally, we need to finish the last step. So last step, we want to show that. So as a big T step, so at the end, our progressive function should be at least omega big N. Yeah. And now here we digress from the book a little bit. Yeah. So I guess because the book is actually doing search function, search version, but well, the decision version is easier than the search version. So, but anyway, I think the book proof is a little funny. So we do a better proof. We also do this proof in many different ways. Anyway, so we are doing decision version. So at the end we will do some projector. So you should actually do a 0-1 measurement on the first bit, but let's be a little more general. So let's assume we do some projector to desynchronous state. So remember we have all this big ball picture where we have yes instance somewhere, no instance somewhere. And so this P is this dividing your ball into two projector. And anyway, so this P should accept or reject our result to do the decision of our big F. So our psi sub big T as a no instance should be rejected with very high probability. That means it accepts with very low high probability. And usually we do the high probability with 2/3, like 1/3 and 2/3. But for convenience here, we say the accept reject probability is 1/9 and 8/9. Okay? And yeah, that's because we are going to start with the bit bad argument. And anyway, that should not change doing like 2/3, doing 1/9 into 1/9 instead of 1/3 shouldn't change our complexity. It just change the complexity by a constant factor, so this should be okay. We can always amplify with just majority counting. And anyway, so this is this side. So our no instance should be accepted with very low probability, and our yes instance should be accepted with pretty high probability. Let's say 8/9. Okay. And this should be true for all x. And okay. And now we have our claim. So we now we write all what we want into this claim. So this is very general. We say if we have any, so we should say projector here. Okay. So for any two state, so this is a claim on any two state A and B. And we say if there is a projector P that separated in this way, so if the A projected on P square is less than 1/9 and B projected on P square is bigger than 8/9, then this distance A minus B square is at least 2/3. Okay, so kind of mental picture is this. So we have A and B, and B is allowed in this P space, and A is allowed in this 1 minus P space, identity minus P space. So remember, if P is a projector, then identity minus P is also a projector. So the space can be, so the whole Hilbert space is kind of separated into P and 1 minus P. Okay. So here we have, so I should write this here, right? So we have this line, and you will partition your space into P and 1 minus P, and so P should be yes instance, and 1 minus P should be all the no instance. Okay, but there are okay. So the only I guess the tricky point here is that this is 1, not 1 and 0. So with 1 and 0, then it's very obvious that the no instance and yes instance are just orthogonal to each other. So and you have different, then you have a distance should be, so if this is orthogonal, the distance should be 2. Yeah. but it's actually not totally orthogonal, so we need to do a little extra work to say that you have this constant gap, you still have this constant distance. And okay, so let's start with the easy version of proof. This is why we need to use this really large gap of 1 and 8/9. And the proof, we are actually going to switch to absolute value of inner product. Okay? Because it's actually easier to do this now. And anyway, so we want to consider this absolute value of inner product between our vector A and the vector B. And so A and B satisfy this relation and this relationship. And now you notice that the whole space is separated into P and 1 and P, right? So B has a very high low overlap with P. That means B has a very low overlap with 1 minus P. Because you add this number and this number, it should become 1. So B projected on 1 minus P should be less than 1/9. And that means if you don't do this square, then that should be less than 1/3. And so yeah, so now we start to separate our AB inner product. And first thing we do is we insert the identity, and then we separate the identity into the P and the 1 minus P part. Okay. Then we do triangle inequality. So yeah, so because it's a summation here, then it should, you can separate this A 1 minus P B. Anyway, so this is just, so you have A and B sandwiching 1 minus P and P. Then by linearity is just A B sandwiching 1 minus P and A B sandwiching P. And then triangle inequality, this absolute value, you can just add both absolute value here, the upper bound. And then you do more triangle inequality. So this absolute value of A 1 minus P B, you can separate into this vector, this A vector, A bra inner product with 1 minus P and B. Okay, right? And so the absolute value of inner product of those two vectors. Okay, so this is actually not triangle inequality. This is Cauchy-Schwarz. Okay. This is less than absolute value of A times absolute value of minus PB. And here we are being lazy of not writing the cat here. And similarly thing, okay, I guess I can keep this. And similarly thing here, so we have A, P, and B. Right. And I guess the little thing we need to notice here is we are keeping our parentheses on different sides because you want to parentheses one with P and B and A and P because those are small, right? We want to show the inner product is small because we want to show A and B are far away from each other. And yeah, then that's what we do. So this is a very crude estimate. So the absolute value of A is obviously upper bound by 1, absolute value of B is upper bound by 1. And this thing, as we show up here, is less than 1/3. And the other thing, so P with A, then it's from here, right? So the component of A on P is less than 1/9, and if you take square root, it's less than 1/3. So less than 1/3 and less than 1/3. So total is less than 2/3. And but that's the inner product. Then we are going to show the thing that we keep saying. So inner product, so upper bound on inner product can be turned into a lower bound on this distance square. And just do this by expanding everything out. So A minus B non-square is equal to A squared plus B squared minus A inner product B minus B inner product with A. Okay. Yeah, then this is 2, and then is bigger than because then you add absolute value on those two terms, so that's bigger than you are subtracting the absolute value of AB inner product. And we show that any AB inner product is at most 2/3. So this is at least 2 times. Wait, did I make a mistake here? Okay, I think it's correct. Yeah. So this is equal to 2 times 1 minus AB. And this part is at least 2/3. So the whole thing is at least 2 times 1/3, so at least 2/3. Okay. So this is a very crude estimate. So that's why we need to amplify this to 1/9 and 1/8. But anyway, now we can complete our proof for global lower bound. So assuming at the end our algorithm is accept and reject with this probability, then at the end of the algorithm, so we put our AB back to our psi t and psi xt, then the progress at the end should be at least 2/3 for every pair of these psi t and psi xt, and you sum over all x so that it is 2/3 n. Okay. So the end, the progress is at least omega bigger as we claim, and that means t is omega square root n as we claim. Okay. Any question? Otherwise, we will. So this will complete the proof of our Gaussian algorithm, but we are a little unhappy about this proof. It's not pretty enough because we need this weird amplification, this weird gap of 1/9 and 8/9. And yeah, so actually this plan here is not tight. Okay, so we are going to give some argument about tight way to do this plan. So when okay, so the actual claim we want to have, so when we do this with a beta argument, the type claim is that if you have, so we are still having our state A and B, and still projector P, and separating the space into P and minus P. So if so A and B, so let's repeat it here. So B is on P and A is 1 minus P. So if the gap is like epsilon and 1 minus epsilon, okay? So excuse me. So for some epsilon in, I guess, epsilon in 0 to 1 over 2. Right, so this is a possible error. And anyway, so then the inner product between A and B should be upper bound by this function epsilon, that's 2 times square root epsilon times 1 minus epsilon. And yeah. So in particular, this function when epsilon equal to 1 over 2, I guess when epsilon equal to 1/3, then is, you can try it, 2 square root 1/3 2/3 equal to 3 over 2 square root 2 equal to square root 8 over 8. Nice. But anyway, so if we have this, then even for epsilon equal to 1/3, we still have inner product between A and B bounded away from 1. Whereas if you do this, then I believe, yeah, here if you do 1/3, then number is going to be, you are not going to be able to bound this by less than 1. Okay. And okay. Anyway, this is actual type number, and we are going to show from several different angles why this is true. This will be a small introduction on information theory. Okay. And so the first proof is we just do basically this thing but better. Okay, so we have it here. So yeah, as we say, we change to epsilon, and the actual bound is 2 square root epsilon times 1 minus epsilon. Yeah, so we start with a similar thing. So we want to bound the inner product between A and B. So inner product between A and B, and then we insert I minus P and P in the middle. But we also use that P and I minus P are both projector. So P equal to P times P, and I minus P equal to I minus P times I minus P. Okay. And then we do similar thing. Then we do Cauchy-Schwarz. So the norm of this thing is less than norm of this, and this, right? But here we're switching the order because we know what we are going to do next step. Okay? Doesn't matter because it's multiplication. So next step we are going to do Cauchy-Schwarz, as you may expect. It's a Cauchy-Schwarz of dimensional 2. So we say x1 times x2 plus y1 times y2 is less than square root x1 squared plus y1 squared plus times square root x2 squared plus y2 squared, right? Because the first vector is x1 y1 and the second vector is x2 y2. The Cauchy-Schwarz. And well, we set up this exactly. So this is x1, x2, and then y1, y2. Okay. Then so Cauchy-Schwarz is less than x1 squared plus y1 squared times x2 squared times y2 squared. Okay, and yeah. And now we assume we introduce extra notation. So we say, what if this number is called x, right? And we see this term and this term have actually very high correlation because we still remember those projectors are like measurement. Then you see this term plus this term should equal to 1, right? Because it's a projector on P, and so it's a probability of A on P and the probability of A on 1 minus P, so those two probabilities should sum equal to 1. And also this term and this term should sum equal to 1. So because of those, so you see that this whole thing and this whole thing should sum equal to 2. So if we call this as x, then this should be 2 minus x. So the whole thing should be less than 2x times 2 minus x. Square root x times 2 minus x. Yeah. And then we are almost finished. Then we remember x is actually less than 2 epsilon, because that's how we set things up, right? So yeah, just here, right? So this A on P and the B on P minus 1 is less than, both are less than epsilon. Okay. So x is less than 2 epsilon, and we are being rigorous here. So x is less than 2 epsilon, then square root x times 2 minus x is actually less than epsilon, excuse me, is less than square root 2 epsilon times 2 minus 2 epsilon, because wait, is this? No. So we need to be a little careful. So we need to make sure this function is monotone on x, because x is less than 2 epsilon, but then 2 minus x is actually bigger than 2 minus 2 epsilon. But if we plot this function, so x times 2 minus x, and so this is actually a quadratic function, and with a peak on x equal to 1. And so you plot this parabola, then you see that this function is increasing between when x is between 0 and 1. So you know that when x is less than 2 epsilon, then this function is less than its value when x is equal to 2 epsilon. Okay. So it's increasing, so when x is less than 2 epsilon, then this inner product absolute value of the inner product is less than 2 epsilon times 2 minus 2 epsilon, and this is what we said we should get 2 times square root epsilon times 1 minus epsilon. Okay. And this needs to be true. Want this to be true, then these 2 epsilon should be between 0 and 1, and it means epsilon should be less than 1 over 2. And that makes sense, because you don't want your measurement error to be bigger than 1 over 2, right? Okay. So that's an algebraic way to prove this by doing all the inequalities more careful. Any question? If not, then let's do the 2 different views. So proof number two is actually not rigorous. That's why we have a quotation mark here. Okay? Proof number two is just thinking about, it's kind of a geometric. Then we are thinking about what are actually the base measurement you can do to distinguish a state A and a state B. Alright. So we are thinking we have two states A and B, and they are not orthogonal to each other, so it's a little hard to distinguish them. And so they have some angle here, and now you think about what are the base measurement you can do to distinguish A and B, and A and B are just two vectors, so actually we only care about this two-dimensional space spanned by A and B, right? So we just think about what P do on this two-dimensional space. And you can try to place this thing around, and so intuitively we'll think this very symmetric setup should be probably best. So your P will have this, in the two dimension you will have these two outcome measurement, and the first outcome being 0 and the second outcome being 1. So the 0 is actually corresponding to P, and the 1 corresponding to minus P. And this angle between 1 and the A and the angle between 0 and the B should be about the same. And the angle we call it delta. Okay? So you see when delta equals 0, then we are perfectly distinguishing A and the B. And when the angle between A and B gets smaller and smaller, then it gets harder and harder, because then the probability of B getting to 1 or A equal to 0 are getting bigger and bigger if they are say in the middle, right? And anyway, so that's the sketchy part. So we argue this is the base measurement we can do, and let's see how this measurement actually do. So the error probability is the probability of B equal to 1 or A equal to 0, and you can just read the geometric here, then that should be sine squared this delta. And and as our and as our promise said, the error probability should be less than epsilon. Yeah. So if sine squared delta less than epsilon, then what's the I guess it's about epsilon, because everything is not rigorous here. And so we know this angle is characterized by sine squared delta about epsilon. Then what's the inner product we want to bound? So the inner product between A and B and absolute value, we can also do by trigonometry. So the inner product should be cosine of their angle, and the angle is pi over 2 minus 2 delta, because everything is pi over 2, then there's a delta and another delta. So it's pi over 2 minus 2 delta. And then now it's just trigonometry time. Then cosine pi over 2 minus 2 delta, that's sine 2 delta. And sine 2 delta we can break into sine delta and cosine delta. Yeah. And so here is another thing we don't do very rigorous, because we know sine delta is less than this, but one way increasing, one way decreasing. But anyway, sine delta, so we are being stoppy here, we just write delta sine. And anyway, sine squared delta is about epsilon, and cosine squared delta is about 1 minus epsilon. Sorry, 1 minus is about 1 minus epsilon. Then you take square root of everything, then that should be about 2 times square root of epsilon, 1 minus epsilon. Okay? Although the direction of this inequality is actually wrong, so want to prove this, then you need to be more careful and where is it? Wrong this argument again. But this is kind of sketchy, so just give you an idea that you can see this in geometric way. Okay, question. And the last one we use, no, this is very far away. So it's rigorous, but you use a concept that we don't formally introduce in our class. But it's pretty cool. So hopefully this give you some incentive to read the later chapter of the book. So this is using some results in the information theory part of the book, and particularly in chapter 9. And the important thing here is those two concepts. So there are two nice quantities that people use to check the distance between quantum states, and they are called trace distance and fidelity. They are actually generalization of what's it called? Some classical distance measure between probability distribution. But anyway, we don't have formal. Okay, and we know something between. We know we are going to use some factor on trace distance and fidelity. We are not going to prove, but we just state here. And trace distance, so we can actually give a formal proof of trace distance. So it's very simple here. So trace distance is called trace distance because it's a trace of the distance. So but it's easier to return in terms of density matrix. Okay, so both trace distance and fidelity are defined on Bing states, but obviously, so hopefully you remember. For pure state, then the corresponding density matrix is just a projector onto your pure state, right? So we have our pure state A and B. Then there is a density matrix rho 1 that is A cat A block, and another density matrix. So I should say like rho A and rho B. Okay, rho B equal to this projector PB, and the trace distance is just you take the difference between those density matrix. Okay, that's another matrix, although you will have negative and positive. Then you take the absolute value of this density matrix. That means then you take trace. Okay, so it's easier to say the absolute value and trace together. So absolute and trace means that so you have some matrix here, then you just sum over the absolute value of all its eigenvalues. Okay? And there is another one more too because you want these numbers to be 0 and 1. Okay, so that's the mathematical definition of trace distance. And what's cool about it is that it has a very operational meaning. Okay? And so the trace distance is actually the upper bound on the maximum maximum measurement probability to distinguishing A and B. And in other words, it's the upper bound on the bias between measurement probability of input state and input state B. Easier to explain in our notation here. That means we have this binary P and 1 and P measurement trying to distinguish A and B. Then the probability, we'll be saying the probability of getting P should be one of them is 1 minus epsilon and another is epsilon. And this difference cannot be bigger than the Euler trace distance T. Okay? And the difference is obviously 1 minus 2 epsilon. Okay? So it's upper bound on this bias. Okay? So it's very operational. It means how good you can distinguish in your state A and B. Okay? So if the trace density is 1, then you can distinguish with perfect probability. So if trace density is 1, then one of them can be 1 and one another be 0. And if it's 0, then they are the same state. If trace density is 0, then they are the same state. And whatever measurement you do, you will get the same probability distribution. Okay? So that's trace distance. Keep it on the eye here. And so effect 2 is effect, actually write 3 effects here. So effect 2 here is about fidelity. So what's fidelity? The fidelity on density matrix is actually quite complicated, but fidelity on pure state is very easy. It's just the inner product with the absolute value. Okay? So that's kind of why we keep calculating the inner product, because it's a very nice quantum information quantity. Okay? Now this is fidelity. Oh, excuse me. Okay. Hello, can you hear me? Yeah. So our inner product is their fidelity, and for pure state, there is this very nice relationship between fidelity and the trace distance. You can translate between each other directly. Fidelity squared plus trace distance squared equal to 1. And I guess it makes sense in terms of the extreme, right? So when the distance trace distance is 1, that means the states are orthogonal, and the fidelity, the inner product is 0. And when fidelity equal to 1, then that means the distance between the states is 0. Okay? And but obviously there are other situations, and you need to run some proof to show that this is true. Okay. And anyway, so just from those 3 lines, now we can show what we want to show. Because what we want to calculate is, as we said, is just a fidelity. And from this relation, we can translate fidelity to trace distance. Just move this around. Then fidelity is just equal to square root 2 1 minus trace distance squared. And we can further translate trace distance. I guess we can bound trace distance by this bias in measurement probability, right? And it's not quite biased. Trace distance is already biased. But anyway, we can translate trace distance to this epsilon. That's error probability when you do our distinguishment measure. And so that's plug in, then it's 1 minus 2 epsilon squared. And now it's just calculate. Now it's just algebra. Then you have 4 epsilon minus 4 epsilon squared, and you see that this is exactly what the result we want. Okay, so almost no calculation here. Everything just from this relationship. Okay, so I think that's enough for today. We have finished every detail of our Grover algorithm proof. I guess we can. We have a little more time, right? So we can do this bound a little better. So we have shown this a lot. So if we plug this back into our Grover algorithm, that means when we use if epsilon equal to 1/3. So now we don't run this extra 19 epsilon. So we do epsilon equal to 1/3. Then let's see if I can do this. A, B is less than 2, and we say square root 3 over square over 2 equal to square root A over 9. And then we can run. Then we run this parallel. We can have b square is bigger than 2 times y minus square root a over 9. Okay, and is some number. Is some number c. Okay, is some number that's bigger than 1. And I guess we can Google, but yeah. And then so instead of this 2 over 3, we will have our dt is bigger than, let's call this number c, c times n. Okay. Okay. So that's the proof of our optimality of global algorithm. And next time we have some extra thing to say about global algorithm, and say it's our function, and we can say some application about it. Show how to plug in algorithm or global search into all kind of different things to construct more interesting algorithms. Okay, then if there is no question, let's stop early today, and see you next Monday.